Good afternoon, everyone. My name is Rajat Bonik, and I am one of the PMR research scholar at IIT Dhanbad, also a TA in this foundation engineering course conducted by uh, Nptel and taught by Professor Dilip Kumar Vaidya sir. I am one of his TA, and I have also 6 months of teaching experience in NPTEL as a TA, and my previous course was uh, ground improvement, which also conducted by Professor Dilip Kumar Vaidya sir. So today we are in week 8 of this foundation engineering class. We also completed the shallow foundation, then earth retaining wall concept. That means earth pressure concept, active earth pressure, passive earth pressure. And today we now start the deep foundation with the pile foundation. And in one or two points I mention here that this session is recorded and it will share to everyone through YouTube, uh, through NPTEL in my YouTube channel, and also whatever I am discussing here, the materials I will share to everyone in my Google Drive. You can access it and later on. Uh, so, and if any unforeseen happens, that means network problem is happen or any other things, don't worry. I will try to solve this problem very quickly and join again. Don't leave the meeting. So, in our today's session, we discuss these the lectures of week 8. There is 5 lectures, and we first discuss the theories and whatever in the PPTs we discuss, and then try to solve previous year questions. First, we solve the 2020 previous year questions, and then we try to solve the 2023 previous year question. So let's start our session now. Or uh, oh, I think we now start our session. So I am sharing my screen. Please wait. I think it is visible to everyone. The screen is, I think, visible to everyone. So let's start with the lecture number 36 of this week 8. So in lecture number 36 is belongs to, or we can say it is the summary of this retaining wall, stability analysis of retaining wall. That means whatever we discuss in regarding the earth retaining wall, we will just shortly conclude here. So in if we further move on to retaining wall stability, we find different types of stability wall, like a reinforced earth retaining wall, or I think geosynthetic earth retaining wall. For different type of earth retaining wall, there are different formula to find out the factor of safety against the failure of this retaining wall. And here is given one factor of safety for reinforced earth retaining wall. That means in slope or retaining wall is combined with the soil and also the reinforced material like steel or any other reinforcing material which is take care of the tension on this soil, because we know that soil is very weak in tension. So this reinforced material is help to take care the tension of the soil and reduce the failure of this retaining soil material, which can backfill or we retain by this type of work. So here it is given the factor of safety of this reinforced retaining wall is gamma z 10 delta 2 into L into W divided by gamma z k s into h, where gamma is the uh, gamma is the unit weight of the soil, z is the depth of this retaining wall, 10 delta is the friction coefficient of this retaining wall, and L is the length of this, you can say, failure from the or reinforcement length of this reinforced retaining earth retaining wall. W is the width of this, or you can say thickness of this reinforced material. S is the vertical spacing. H is the horizontal spacing. K is the active earth pressure coefficient. So by this formula, we can easily derive the factor of safety of this type of retaining wall. Then we can come across this type of difference in our previous class also. That is active case and passive case. We know that in active case, wall moves outwards the backfill material, and in passive case, wall move inwards to the backfill material. And we also know that shear stress on the failure surface of plane reduce in active case, but in passive case it is increased. Lateral pressure also reduce in active case, and passive case it is increased. Minimum lateral stress achieved when the soil fails and full strength is mobilized. In active case, maximum lateral stress achieved when soil fails and full strength is mobilized. So these are the difference between the active case, the active earth pressure and passive earth pressure. We also come across these differences. Then again, we also study the different type of failure of this retaining wall. That means in different earth pressure. That means earth pressure is stress. There is no failure of this backfill material. But in active case also, in passive case also, earth pressure is fail. In active case, the failure surface is make an angle which horizontal is 45 degree plus 5 by 2, and in passive case, the failure plane is make an angle which horizontal is 45 degree minus 5 by 2. So these are the Mohr circle diagram for different types of earth pressure. It is for earth pressure at rest. This is for active earth pressure. This is for passive earth pressure. So in active earth pressure, horizontal pressure is less than the vertical pressure. In passive earth pressure, horizontal pressure is greater than the vertical pressure. So according to this, the major and minor principal stress also changes. So in active case, the major principal stress is vertical stress and minor principal stress is horizontal pressure. And in passive case, major principal stress is horizontal pressure and minor principal stress is vertical pressure. So by this we can conclude that in active earth pressure coefficient, that is Ka, is less than 1, because we know that earth pressure coefficient is equal to sigma h, that is horizontal earth pressure and divided by vertical earth pressure. So we can say that in active case it is less than 1, in passive case it is greater than 1. So Kp. Uh, then We also discussed this critical failure plane is 45 degree plus 5 by 2 for active case, and then active pressure force, or we can say thrust, is equal to the half gamma v square into k, where k is nothing but the active work pressure coefficient, which is equal to the 1 minus sin phi divided by 1 plus sin phi, or we can say tan square 45 degree minus 5 by 2. Then in passive earth pressure, it is the inverse of this active earth pressure coefficient is inverse of the active earth pressure, that is 1 plus sin phi divided by 1 minus sin phi, or you can say tan square 45 degree plus 5 by 2. And critical failure plane is 45 at 45 degree minus 5 by 2 angle. Then we can find this formula with the help of Mohr circle also, and here we can see also that this derivation, by this maximum failure point derivation, we can solve the passive earth pressure or formula, or find passive earth pressure formula and active earth pressure formula. So then we can also learn that if the backfill material is not horizontal, that means the surface of the vacuum material is at an angle of I, then there is a change in active earth pressure coefficient and also passive earth pressure coefficient. In active earth pressure coefficient is equal to, the active earth pressure coefficient is equal to cos I minus root over cos square I minus cos square phi divided by cos I plus root over cos square I minus uh, cos square phi whole into cos I. And in a passive earth pressure, it is the inverse of the active earth pressure coefficient. And if you put I is equal to 0, we can get that k is equal to 1 minus sin phi divided by 1 plus sin phi. So we can conclude that if the horizontal, if angle is equal to 0, it is nothing but we come the basic formula with where surface is horizontal. Then, if again we also learn that if there is, the previous formulas are only for uh, cohesionless soil, but if there is present cohesion also present, that means C5 soil, the formula is changed, little bit changed. That means for uh, active earth pressure, the pressure at below the wall or at the bottom of the wall is equal to the uh, sigma 1 K minus 2C root over K, where sigma 1 is the vertical stress and C is the cohesion, unit cohesion in the soil. But and it is in passive case, it is changed and it is equal to sigma 1 Kp plus 2C root over Kp, where again sigma 1 here it is vertical stress and C here to C unit cohesion. And then now it is, I think, over earth pressure, uh, or can say earth retaining wall theories are over, and also we done some example problems also and previous year assignment problem also for regarding to these theories. Now we move on to our next lectures, in the next lecture in week 8, which is lecture 37, and here one we start with the deep foundation, and we specifically study the pile foundation, which is one of the one of type of the deep foundation. So, and this pile foundation is more popular among these all deep foundations. So we study now deep foundation, especially the pile foundation. So in we know that the shallow foundation, the foundation is classified into two types, that is shallow foundation and deep foundation. So the shallow foundation require less expensive, better for useful for better uh, lighter structure on less problematic soil. Typical types of shallow foundation are spread footing and rafts and mats. But in deep foundations are more expensive, typically used for heavy tall structure on more problematic soil. And typical types are driven piles, drilled piles like that. Then design requirement for this type of foundation or any type of foundation. So first we come across uh, two major component for our designing. One is safety, another one is serviceability. So safety, there should be adequate bearing capacity, which bearing capacity in the soil, which take care of this structural load. So this for safety, the adequate factor of safety against the shear failure, and we know that main soil is fail mainly due to the shear, and soil is very weak in shear, and major of this soil failure are occur only through the shear failure. So we safety we take against the shear failure, and you can find this shear failure by dividing the factor of safety, uh, divide by dividing the ultimate bearing capacity with the factor of safety, where Q is the bearing pressure. For serviceability, we consider the extractable magnitude of the settlement. So due to the settlement, if it is exceed to a certain limit, there may be generated the stress on the structure at a specific location, mostly in the corner or joints on the mm, pile and joint on the column and beams. So due to the stress, there may be possibility to generate cracks due to the stress concentration, and structure may fail due to this cracks. So we have to limit our settlements during our construction by providing some providing better requirements which is needed for designing this foundation. And this type of settlements may be immediate settlement, which is mostly elastic, and plastic and secondary compression settlement, which is mostly plastic settlement. And secondary settlement are mostly the creep settlement or creep uh, like that. Then there is one term is called allowable bearing capacity, and allowable bearing capacity is the maximum load which satisfies both the conditions, safety as well as serviceability. That means the allowable bearing capacity is that type of bearing capacity which can save against the shear failure also, and which also save against the uh, settlement also. So this bearing capacity is called allowable bearing capacity. Then there is pile foundation. So we already know that the pile foundations are more expensive. That means it is require more money to construct pile foundation than the shallow foundation, any type of shallow foundation. Then use to get acceptable bearing capacity and settlement. So we mostly use this pile foundation where there is a requirement and for structure to safe against bearing also and safe against settlement also, and typically used for larger structure on more problematic soil. So also this type of where the soil condition is very poor or problematic, we can use this pile foundation. Then why we need this type of pile foundation, or you can say deep foundation? What is the requirement to use this deep foundation? So here it is said that the fill or pore soil condition near the surface, so that excavation for footing, mostly shallow foundation, would be difficult and expensive. So we can use deep foundation, mostly tile foundation. Then ground permeabilities and groundwater condition likely to make it difficult and expensive to exclude water from the excavation. So so then also we can use this type of foundation. Then again, to get an acceptable bearing capacity, which may be difficult to achieve by a footing foundation. So requirement to fulfill our bearing capacity requirement, we use this reef foundation. Then again, to keep the settlement within an acceptable limit, which may be difficult to achieve in footing foundation, and again the foundation to carry heavy columns load. So these are the condition, and there may be a continuation also. That is, these are foundation required to take large uplift force, where tension piles may be cheaper than providing the necessary footing size with the mass to resist uplift. So due to, in we can say in mostly in clay soil has the nature of expansion and we can say construction due to the presence of water or moisture. So in clay soil, if you build in any structure, there is possibility in summer the soil is may get contract due to the evaporation of water in the soil, and in rainy season it may get expelled due to the presence of the water or moisture. So due to this expansion and construction, the structure which is built on this type of soil, this type of problematic soil, may get damaged, and there may be generation of the tension, and structure is failed by the tension or uplift due to this type of soil. So to address this type of soil, we can use the tension pile to take care of this type of uplift forces. So that's why we need sometimes this type of pile foundation. Even if uh, nothing is happen, uh, even if the soil below the structure is stronger, but if there is a presence of clay type nature of soil, then we can use mostly go with the pile foundation to resist these uplift forces. Then again, foundation required to be stiffer than can be achieved with footing or raft. So if we go with the most stiffer foundation, we can go with this type of sorry. Sorry for the convenience. So we can start again. So again, if you need the stiffer foundation, then shallow foundation, so we can go with this type of deep foundation like pile foundation. Poor soil condition where ground improvement techniques may be proved more expensive than the pile. So if you address this poor soil condition by ground improvement technique, sometimes it require more cost or more expensive than using the pile foundation. So better to go with this type of deep foundation without improving the ground. So these are the condition need to be checked why we use or need this pile foundation. Then different types of deep foundation like pile foundation, deal pile, and caisson. So function and feature are similar. Okay, and each typically subjected to an axial. Sometimes piles and caisson serve as a anchor for pressure installation. Then difference is primarily in their physical size and the method of installation. So only difference is their physical size and shape and method of installation. Now pile foundation, specially installed relatively slender columns. Uh, वाईफाई चल रहा है क्या? मुझे तो काम नहीं कर रहा। तो नेट चल रहा है क्या? नेट नेट नहीं चल रहा। तो बंद करके देखो तो। बंद कर। तो नेट तो ना काम नहीं कर रहा। कौन सा है? हम्म, काम कर रहा है क्या वाईफाई तुम्हारा? काम तो नहीं कर रहा। ओके। तुम्हारा वाईफाई चल रहा है क्या? तो डाटा बंद हो गया। हेलो। हेलो। ओके, इट्स फाइन। So sorry for that. Network is disconnected. So I think we will again back to this online and we start again. So we are coming in that in different types of deep foundation. So in deep foundation, we say that three types of deep foundation. One is piles, drill, and another one is cushion foundation or drilled piers. So in pile foundations are specially installed relatively slender columns used to transmit structural loads to a lower, firmer soil and or rock formation. The diameter is generally less than 750 mm, and the pile may be concrete, steel, timber, or a composite of steel and concrete. Then uh, drill prior or caisson foundation. This uh, this is in general sense of drill prior. Caisson are larger piles, usually 750 or more in diameter. The term drill piers and caissons are frequently used interchangeably by engineers. For drill piers, typically a shaft is drilled into the soil, which is then filled with concrete. The shaft may be cased with a metal shell in order to maintain the shaft from the collapsing. Again, the casing may be left in the place as a part of the pier, or it may be gradually withdrawn as the shaft is filled concrete. The lower part of the shaft may be uncut or belt out to develop a larger end bearing area, thereby increasing the capacity, or we can say bearing capacity of the pier. Typically, drill pier and caisson are designed as end bearing members, and we classified pile foundation based on the material. So there may be timber pile, steel pile, concrete pile, or composite of steel and concrete. Now move on to lecture number 38 of this pile foundation wicket. Here again, here it is given the selection of the selection criteria for pile foundation. So we have need to consider during selection of the pile or material selection, we need to address, or we need to uh, consider the corrosive property of the stratum. We need to find the fluctuation in water table, ease of installation, length required, availability of material, installation equipment, restriction in driving noise and vibration, and cost. Now, customary design note for pile. So here for wood, the maximum load it can take 15 to 30 ton. For composite material, it can take 20 to 30. For cast in place concrete, it is take 30 to 50 ton. And precast reinforced concrete, it is take again 30 to 50. And steel edge section, it is take 30 to 60. Like that, for different types of material, the values are changed, and it is so that see that for steel pipe concrete field or steel edge section give better capacity than any other of material. Now, pile type and available maximum length for steel edge and pipe types of pile, the ultimate length is the short section are driven and additional section are filled welded to obtain the desired length. For steel shell and cast in place, this distance are in between 100 to 120 foot. Like that, for different types of pile foundation based on the material, the length also may get changes. Now, classification of pile foundation based on the function. So they are classified based on the function are end bearing pile, friction pile, tension or uplift pile, composite pile, compaction pile, anchor pile, batter pile, laterally loaded pile, and sheet pile. So the end bearing pile are used when there is the presence of soft nature of soil below the structure, and but there is a at a certain depth there is a presence of hard stratum. So due to this presence of hard stratum, the soil, the pile transferred the load directly to the hard stratum. Uh, so this type of pile is called end bearing pile. Friction pile are this type of pile which is transfer the load to the soil from the structure uh, through the side friction of the pile. Uh, then tension and uplift pile. So problematic soil like expensive soil like clay where there may be occur expansion and construction. Due to this expansion and contraction, a tension or uplift generated. To resist this, we can use tension pile, which is take care of this. Then compaction pile. So this compaction pile mostly used in ground improvement techniques. So this compaction pile, actually the main purpose of this compaction pile is to compact the surrounding material by while driving this type of pile. Then anchor and batter type of pile are mostly used to uh, use in anchoring nature or to retain the soil uh, in slope. Then lateral loaded pile. So this lateral loaded pile are mostly used to resist the horizontal pressure. The sheet pile, this sheet pile actually in sheet nature, it is mostly used in the offshore area to resist the or to protect the bank or we can say offshore bank of from the wave wave energy from which is coming from the seawater. Then here it is shown the different types of pile foundation based on the function. It is n bearing pile. The most of the load is bear by this harsh strata through the pile. So it is called n bearing pile. This type of coefficient pile, most because it is load are transferred only through the friction of this pile. Then there is compaction pile, mostly used to compact the surrounding soil. And then tension pile, or we can say fender piles, which is used mostly to take care of tension. Then sheet piles and batter pile, which is also used to in retaining structure. And this sheet pile is used in the offshore to protect the offshore. Then classification based on installation. So there is driven pile and cast in situ pile. Driven pile, by driving in the pile, we can install the pile. So we can this is called driven pile. Cast in situ means we bore a hole and then place casing on it and pour the concrete material, steel material on it, and by this we construct the uh, pile. So this is called cast in situ pile. So here the installation method are mostly driven pile, most common method, where you use steam hammer, diesel hammer, and vibratory hammer. Jet driven pile, where you use forced water before pile to ease placement, good for sandy material and always dry without jetting, last 10 to 15 feet. Then agar pile, which is used for cast in place and to drill through the obstacle. Always record blows per feet, eventually blows per inch. Check the So for driven pile, the maximum driven resistance are for timber, it is 4 to 5 inch blows per inch. For concrete, it is take 6 to 8 blows per inch, and also for reinforced concrete, it is take 12 to 15 blows per inch. Then to measure the pile capacity, we use the two methods to first find out the single piles and also find out the piles in group to find out the total capacity. So first we find out in our upcoming formulas, we first find out the pile capacity for single pile and then multiply by number of piles to get the total capacity for pile groups, piles in groups. So for single pile, if the load transfer mechanism are through friction or through end bearing or also both friction and end bearing. So here it is given axial load capacity of this single pile. So it is divided into two parts. One is friction, another one is end bearing or tip resistance. So the friction resistance is defined by the friction stress in multiplied the surface area of this pile, and of course the friction resistance. And tip resistance force we can find out by the tip resistance multiplied the bearing area of the tip. So this friction resistance is dependent on different types of soil. For clay soil, it is different. For sandy soil, also it is different. Same types for tip resistance is different, also different for different types of soil. Now moving to the lecture number 39 of this week 8. So here it is said that the allowable force required to design this pile is nothing but the ultimate load which is taken care by the pile divided by the factor of safety. Now here it is said that the load is transferred to the soil surrounding the pile by the friction or adhesion between the uh, soil and the sides of the pile, and or the load is transferred directly to the soil just below the pile tip. And this can be expressed in the equation as follows, that is ultimate load is equal to the friction load plus tip resistance. And I think these terms are we already discussed in previous slides, so you can go through it. So for end bearing piles, tip resistance or tip load is predominant, and friction pile, the friction load is predominant. Now we find out for different types of pile capacity for different types of soil. First, we go with the sand soil. So the total capacity for sand is any type of pile is the summation of the friction capacity and end bearing capacity. Now, for sandy soil, uh, F or friction resistance is evaluated by multiplying the coefficient of friction between the sand and pile surface, that is tan delta, which is also depend on the phi and angle of internal resistance of phi by the total horizontal soil pressure acting on the pile. So we in our previous or lectures we find out the horizontal pressure. This is nothing but the earth pressure at rest, earth pressure, active earth pressure, and passive earth pressure, and which is also a function of the vertical stress. So by multiplying the coefficient, earth pressure coefficient, we find out the earth pressure stress. After that, if we find out the earth pressure thrust along this length, we find and again multiply the 10 data, we can get this F friction resistance for different types of pipe. Now for friction for different type of material, the standard data is varies. For concrete, this tan delta is 0.45. For wood, it is 0.40. For steel, it is for smooth surface, it is zero point 0.2. For steel, rough surface, it is zero point 0.4. And corrugated steel, it is 10.5 of cent. Now, here it is mentioned that the horizontal pressure, the total horizontal pressure acting on the pile is a function of the effective vertical pressure of the soil adjacent to the pile. And soil pressure is normally increased as the depth increases. However, it has been determined that the effective vertical pressure of the soil adjacent to a pile does not increase without limit as depth increase. Instead, the effective vertical pressure is increased as the depth increase until a certain depth of penetration reach. Below this depth, which is called the critical depth, is denoted as DC. The effective vertical pressure remains more or less constant. So it is said that if we continuously increase the depth, the effective vertical pressure is increased, which is also required to find out the effective horizontal stress. But at a certain depth, this effective vertical stress is there is no change in effective vertical stress. That means more or less the effective vertical stress is remain constant. So this depth from where the effective vertical stress is constant or there is no change in effective vertical stress is called the critical depth. So we can say that if from the ground surface, if we move towards or below the ground surface at a depth z. After a certain depth, we call dc, this effective vertical stress is constant. There is no further change in this effective vertical stress. So this depth is called the critical depth, and this depth is required to find out the total horizontal pressure along this depth. So we know that this pile friction resistance for sand F is depend on the horizontal pressure force. So and this horizontal pressure force is also depend on the vertical force stress. So it is required to find out the total stress. That means the area along this pile to find out this F. Here the full concept are given in pictorial form. You can see that at a certain depth, this vertical stress, this sigma v is not changed. It remains constant. And here it is one thing is most important thing is given that this critical depth DC is in between 10D for loose soil and it is in between 20D for dense soil. So this is also changed. The critical depth is also changed based on the soil nature. For loose sand, it is loose soil. It is 10D. D is nothing but the diameter of the pipe. Has a diameter of the pipe, and for dense soil, it is 20D. Uh, Now, if we find out the total force of this diagram, we can use this formula. After derivation, it is looking like that, which is total force along the or total friction force along the pile, considering the critical depth for questionless soil or sandy soil. The formula is gamma dc square, which is critical depth, by 2 plus L. L is the nothing but the length of the pile minus dc critical depth into gamma dc into K. K is the earth pressure coefficient into L that is the friction coefficient into pi d. Pi d is the perimeter of this pile. So after that, now we find out total ultimate load of the pile is equal to the friction load plus end bearing load. For sand, we first find out the QF friction load. Now we find out the tip load. So tip load is mostly act like the bearing capacity formula. We use the bearing capacity formula for shallow foundation. But here the bearing capacity effect like NC, N gamma, NQ are different from this shallow foundation. So we see that this Q tip resistance is equal to the Q into A tip. A tip means surface, we can say bearing area or cross sectional area of the pile at the end of the pile. And Q is nothing but the bearing of this bearing pressure of this pile. So it is find out by simply this bearing capacity formula where for friction cohesionless soil it is equal to for circular pile or we can say circular foundation which is the gamma df nq plus zero point 0.3 gamma d m gamma and for square it is only changes here point in place of zero point 0.3 it is zero point 0.4. Now here is one important note is given that it can be noted that this equation have the same general form as the bearing capacity equation of shallow foundation. However, the magnitude of this effective vertical pressure is sorry. The, it can be noted that this equation are same have the same general form as the bearing capacity equation of shallow foundation. However, the magnitude of effective vertical pressure of the soil adjacent to the pile is more or less constant below the critical depth. Thus, the design purpose, the term gamma df nq should be replaced by vertical effective vertical stress into nq, where uh, gamma sigma v dash is the effective vertical stress. Further, it in most cases the driven files are relatively small in cross section. Therefore, the term involving uh, D and B are small compared to the terms of equation. So we can neglect this. So our ultimate formula is for tip resistance is Q is equal to effective vertical stress into NQ. NQ is the bearing capacity coefficient for deep foundation. Now moving to the last lecture of this 8 week. After that we solve the previous year question and here very interesting previous year questions to solve we in our sessions. So we quickly complete these lectures first. So in this 40th lecture, same thing as written here, uh, but here it is said that soil just below the pile tip is displaced outward and upward, causing shear stress to be induced in the soil above the tip. These stresses early alter shear patterns below the tip as compared with those for shallow footing. Hence, the value of NQ of shallow foundation should be increased to NQ star. And the bearing capacity factor of the pile dimension is nothing but same is Q is equal to sigma V dash of T into NQ star. And for finding out this NQ star, which is more depend on the friction angle of internal friction phi, and different type of methods. Like for Mayorov, it gives different value. For Tajagi, it gives different value. So you can see that for 30 degree, the value of this NQ is equal to in between 40 to 60. For 36 degree, in case of Mayorov, it is in between is almost equal to 160. Now the total capacity, which is nothing but the summation of the QF plus QT. So QF is the friction force, QT is the end bearing force. So total load is written like that. Just put all this formula here and we find out the equation. Now in case of driven clay, the formula a little bit change. Nothing, only change is there Q for end bearing and F for skin friction. So the F for uh, for clay soil is equal to the alpha into C. C is the unit cohesion of the soil for clay soil. And alpha is nothing but the adhesion factor, which is also depend on the different types of material. And the value of this uh, adhesion factor. And for soft clay, this adhesion factor is equal to 1. A stiff clay, it is less than 1. And again, for tip resistance, we can use the bearing capacity formula for shell formation for clay soil. But here again, we remove this gamma df term and we treated it as Q is equal to CNC. Where NC value for clay soil in deep foundation is 9. For shallow foundation, it is for shallow foundation it is 5.14 or 5.7. Now total formula, total ultimate load for clay soil is alpha C. Here it is NC is not there, so you can say that alpha C little modification is there. Alpha C pi dl, pi dl nothing but the surface area of this pile C and C and pi by 4 d square, where pi by 4 d square is the cross sectional area of the pile. Now here it is said load transfer plot are given for different types of soil and differ with the depth. So you can see that uh, it is said that more displacement is required to mobilize the tip resistance. So if the movement of the pile is in in a limited zone, that means the movement due to the structural load is in range, within in range, then there may not be generate the tip resistance. Only through the friction of the shaft that or pile, the total load is transferred through the soil. If more displacement is occur, then only the tip resistance is come into this picture. And loss transfer mechanism is shown for pure and bearing piles. You can see that uh, the total Q which is applied on the pile is constant. The total force applied is constant. But for end bearing pile, there is no friction resistance, only transfer through the soil. If the tip is displaced to a particular point, then there is a variation of the pile load or pile capacity and small deflection. The load capacity is small, but for higher deflection, it is may go on increasing. After a certain displacement, it may not change. It's constant. For pure end friction, the total load Q on the pile is very fast. It is more, and after depth, a certain depth, it is become less, or it is become zero. And friction depth by this depth versus skin friction curve is similar to this end friction curve, but the end bearing piles, but it is less below than the end bearing piles. Similar curve plot is also there. See that here is also Q1 pile divided by the pile tip. You can see that. So please wait. Network. So sorry for the convenience. I think the weather is not good today. There is issue of network problem issue. So I think we can wait for 5 minutes. There may be problem may arise. So after that we can again join, and you can treat as a break, 5 minute break. After that we can again join. रिकॉर्डिंग चल रहा है क्या कर सकते कुछ कोई नहीं आवाज रिकॉर्ड होता है बैकग्राउंड रिकॉर्ड होता है डिफॉल्ट कर दिया Welcome again. This session. There's frequently network issue, so I think we now resolve it. And I think our lectures also completed. So now we start with the assignment problem, previous year assignment problems. So we quickly go solve the previous year assignment problem. There is few problems are interesting. So now we try to solve each one. And please stay on the meeting. I will now one by one. I will try to solve it. So first, go to the assignment problem of 2022, sorry, 20. So first question is said that the uses of piles. So we know that the piles, there is different function of the piles for end bearing, skin friction, as used as a uplift and also used as a laterally loaded pile. So the options are given here that it can also use for to carry the vertical load. Yes, it is. Then it can use to resist the flat load. Yes, it is right. And also resist the horizontal or inclined load. Horizontal load in the form of lateral loaded pile, inclined load in the form of lateral pile or anchor pile. And so the correct option for this question is option D, all the above. Now, question number two, it is said that the piles which transmit the majority amount of the load to the pile tips is called. So we know that the pile capacity is divided or based on the capacity pile is two types divided in three types. One is friction pile, another one is Sorry again, today's weather is not good. There is a rain is coming, so I think the network issue are frequently occur due to this weather. So we are again joining the meeting. So we're discussing the problem number two. It is, we know that based on the capacity, piles are divided in three. One is friction pile, another one is end bearing pile, and last one is friction and end bearing pile. So friction pile is transmit the load through the friction of the pile or side friction or skin friction of the pile. End bearing pile resists the load based on the wear transfer the load to the hard stator through the steep which is called end bearing pile and end bearing and friction pile is used both the mechanism that is friction as well as the end bearing. So in question number two, it is said that the majority load if we transmit through the pile tip. So if the majority load is transmitted through the pile tip like that, then it is called, we know that this is called end bearing pile. Correct option is here, option B. Now move on to question number three. It is said that the value of bearing capacity factor for NC for single pile is generally taken as. So we know that the NC value for cohesion soil, NC value for uh, cohesion soil for shallow foundation, we know that by Mayer formula it is 5.14. For Tarjagi it is 5.7. Both these are value for shallow foundation. But deep foundation, this value is changes and it is equal to 9. So our correct option is option B. Then there is one problem is given, based numerical problem is given, which is said that it said that the diameter of friction pile is given 40 centimeter. So it is in zero point 0.4 meter. Then embedded length is given 15 meter. Then and soil is homogeneous consolidated clay soil and cohesion is given, that is C is given 50 kilonewton per meter square. The safe load for we have to find out if the factor of safety is given 2.5, adhesion factor is given zero point 0.7. So we know that total ultimate load QU is equal to the QF plus QB end bearing or T. QF for cohesion is alpha C pi dl. Q tip or QB end bearing is 9C pi by 4 d square. So put all this value here. Here alpha is given 0.7 and C is given 50. Then pi is 1.34, D is zero point 0.4, L is 15. Plus Q a 9 into 50, C is 50 again into 1.34 into D square is zero point 0.4 square divided by 4. So ultimate load is here 1715 kilonewton. So we have to find out the safe. So safe is Q safe is equal to Q ultimate divided by the factor of safety, that is 2.5. So divide this result by 2.5 and get this 286 kilonewton. So you can see that there is no option is available 286, but the nearest option is here given is 264. So our correct option is option D. Now move on to the, I think it is okay to everyone. Question number 4. Now move on to the question number 5. So in question number 5, it is said that a 12-meter long and 300 diameter piles is given in a uniform deposit cell where phi is equal to 38 degree. Water table is given here is greater depth and not likely to rise. Using gamma is equal to 16 kilonewton per meter cube. NQ is given 137 and K is given 2. The ultimate pile load capacity is find out and without considering the critical depth concept. So here we don't use the critical depth concept, directly use the formula. So we know that delta is given 0.75 gamma. So we know that for the ultimate load we have to find for friction for sandy soil. The formula is like that. Again, QS is equal to sigma V dash K delta pi dl plus sigma plus n bearing, it is nq into sigma v at the bottom into pi by 4 d square, it is q b. So if you add both of them, you can give q ultimate. So put all this value, sigma v is here, gamma into z. So put all this value z, or we can say gamma into l. So put all this value. Gamma is given here 16, L is given 12, K is given 2, delta is given 10 delta, or delta is given 0.75 into phi is 38 into pi 3.14. Again D is here zero point 0.3 into L is again 12 plus NQ is given 137 into K is 137 into sigma V. Sigma V is there at the bottom. Effective stress at bottom, which is equal to gamma again 16 into L. L is 12 into 3.14 into zero point 0.4 square. Point sorry, zero point 0.3 square. Diameter is 0.8 meter divided by 4. So answer is 4215. I think I am made one mistake here. I'm again calculated it. Sigma V is here. Sorry. We have to take average sigma V along the shaft. So sigma V dash is average. So for finding out the average, if we draw the line here, draw the fixed stress diagram. Here it is 0. Here it is gamma into L. So the average is 0 plus gamma L by 2. So put sigma average is equal to the gamma L by 2. So which is equal to 16 into 12 into divided by 2 into 2 for K into 10, delta is 0.75 into 38 into zero point 0.3 into 12 plus into 3.14 plus NQ is 137 into gamma into L is here 16 into 12 again into 3.14 into zero point 0.4 square, so 0.3 square, I'm again mistake, 0.3 square divided by 4. Correct option is answer is find out 3036.79. So our answer is 3036.79. So kilonewton and it is almost equal to option B, is 3038. So our correct option is option B. Now, question we move on to the question number 6. So another way we can solve this question number 5, that is we find out the area of this diagram. Here 0, here it is gamma into L, which is equal to, and it is L, which is equal to gamma square half gamma square into L. Then multiply the earth pressure coefficient K. Then multiply the coefficient friction is 10 delta, and then multiply the perimeter of the pile pi d. So formula is gamma L square by 2 K 10 delta pi d plus gamma into L. At the bottom it is again gamma into L into NQ pi by 4 area cosine into d square. You put all this value in this formula, you get directly the result 3038 kilonewton for question number 5. I think it is understood to everyone. Now move on to the question number 6, which is require the concept of this type of concept, and which is also required the data of the question number 5. So in question number 6, it is said that if the water table present at the below the in the problem number 5, if the water table present at a 4 meter below the ground surface, then what is the changes in the ultimate bearing capacity without considering the critical depth concept? And gamma saturation is bulk is given 16, and gamma saturation given 80, and gamma W is given 10 kilonewton per meter cube. So first draw the pressure diagram along the pile. First 4 meter, water table is present. There is no change in the effective stress. So there, because there is no presence of water, so it is gamma bulk into the depth. Here it is h1, here is h2. H1 is equal to 4 meter, h2 is equal to the 8 meter. So here it is gamma bulk into h1, which is equal to 16 into 4, 64. Then after that, so this is same. After that, there is a water present. Due to the water, more pressure generated, and it is reduced the effective stress. So from here to here, we have to find it is again 64. So we have to find this one. So it is equal to gamma dash into H2. So gamma dash is here, gamma saturated minus gamma W into H2 here. H2 is here. So gamma saturation is here 18, gamma W is 10, H2 is here 8. So 8 into 8 is 64. So you can find this also 64. So now we draw this diagram with this value again. So here to here is 64. So if you add this 64 and 64, it will become 128. So here this is 128. So first find out this area of this diagram, total area 1, area 2, which is half 64 into h1. H1 is here 4 plus area of this, it is looking like a trapezoidal. So it is equal to half 128 plus 64 into h2, height h2 is 8. So find out the total area is zero point 0.5 into 64 into 4 plus zero point 0.5 into 128 plus 68, so 64 into 8, which is equal to 896. So total vertical force for thrust is 896. After multiplying with K, we get the total horizontal force. And then if you total horizontal thrust, after then if you multiply the 10 delta, we get the total horizontal thrust act on the pile. But the if we again multiply this with the periphery of the pile, this is pi d, we get the total friction force load in terms of kilonewton. So put all this value 896 into K value is 2 into 10 delta is 10.75 into 5 into that is 38 into 3.14 into zero point 0.3, which is equal to 916 kilonewton. So QS is our 916 and QB is we have to find NQ gamma dash sigma V dash into pi by 4 d square sigma V dash at the bottom of the pile. So we which is 128. So Q NQ is 137 into 128 into pi is given 3.14 and D is zero point 0.3 square. D square is zero point 0.3 square divided by 4. So put all this value 37 into 128 into 3.14 into zero point 0.3 square divided by 4, which is equal to 1238 kilonewton. So add both QB and QF, QS, which is equal to the 2154 kilonewton. So the closest answer is here option D, that is 2156. So our correct option is option D. I think this problem required little bit logics. So I think it is understand to everyone. And no, if you cannot understand in my uh, on online, I also provide the solution to you. Don't worry, just look into this concept first. Now, I think it is okay. So, for this case, we actually first question number 6. We first find out the pressure area of this pressure diagram, which is based on the effective vertical stress, and after this multiply the active earth pressure, passive earth pressure, or earth pressure coefficient K, which is given the total horizontal thrust. After that, if you find out the total horizontal thrust actually act on the pile as a friction, we multiply with it the 10 delta, that is friction coefficient, and if we again multiply the periphery area, we actually find the total load of act on this periphery, or on this side of the pile as a friction, and to find out the n bearing, which is equal to the vertical stress at the bottom into NQ bearing capacity factor into pi by 4 into d square, which is the area of cross section area of this pi at the bottom. Now, then add both and get the answer. Now move on to the question number 7, which is uh, tell that the ultimate it is asked that ultimate load carrying capacity of a 10-meter concrete. Question number 7 is asks that ultimate load carrying capacity of a 10-meter long concrete pile of a square cross section is again there is a problem on network. So I'm again sharing it. Today class is going like that, disturbing for due to the networking. So question number we now in question number 7. So question number 7, it is said that the ultimate load carrying capacity of a 10-meter long concrete pile of square cross section is given for 50 mm by 450 mm driven into homogeneous clay layer. Having the undrained cohesion value is 40 kilonewton per meter square is 700 kilonewton. So this said that the ultimate load is given 700 kilonewton for a cohesion is 40 PA and the cross section is 450 mm by 450 mm and length is 10 meter. If the cross section of pile is reduced to 250 mm by 250 mm and the length of the pile is increased to 20 meter, then find out the ultimate load in kilonewton. So we can see that to solve this problem, there is not given the alpha value, that is cohesion factor or adhesion factor. So first find out the alpha value based on this result, first given result. So which is equal to the Q ultimate is given 7 Q 100 kilonewton, and we know that the total force acting on the pile is for skin section it is alpha into C pi dl and n bearing it is 9c pi by 4 d square. So d is given, d is nothing but the width, or sorry, the last one is it is square cross section. So it is, there is modification, it is actually I'm writing it is for circular cross section. So square cross section it is uh, 4b the perimeter of this uh, pile into L length, and here the cross section area is b square. So put all this value and get the alpha. So C is so if you put this 700, which is nothing but the Q ultimate is equal to alpha here you have to find out into 50 into 4 into B is given here 0.45 meter and L is given 20, 10 plus Q is given so 9 C is again 50 and B is zero point 0.4 B square is 0.45 square. So here we find out 700 minus 9 into 50 into 0.45 square divided by 50 divided by 4 divided by 0.45 divided by 10. So answer is the cohesion factor is 0.67. Alpha is equal to 0.67. Now put this value, use this equation again to find out the total ultimate load for second configuration. So for this alpha we find out 0.67, C is same 50, B is 4 into B is changed here 0.25 meter, L is given is here again changed 20 meter plus 9 into 50 plus pi by 4 into pi by 4 into D is sorry pi by not pi by 4, B square is 9C into B square, B is here again 0.25, that is 0.25 square. So find out this 0.67 into 50 into 4 into 0.25 into 20 plus 9 into 50 into 0.25 square. So the total load is 6. I think there is a little mistake here. I'm again calculated finding the alpha. 700 minus 9 into, sorry, C is here 40, not 50. So there is modification. It is 40, not 50. 40. So again find out the alpha. I missed do a mistake here. So 9 into 40 into 3.14 into point sorry 3.14 not 3.14 9 into b square b is 0.45 square again divided by 4 divided by 40 into 4 into so divided by 0.45 divided by length 10. So alpha is coming out 0.87 not 67. After finding out alpha, if you multiply it and put second formula, it is alpha into C 40 into 4BL 4B 0.25 into L is here it is 20 plus 9 into 40 into 3.14 into 0.25 sorry not 3. B square so 0.25 square which is equal to 197 so 719.27. So the correct option is or closest option is option C. So the correct answer is here option C. I there is changes is here. I am using first is 50 as in the place of C, but it is given here 40. So please uh, check the result again and do it properly. I'm after finding replace the put the correct value I am getting 719.27. So correct option is here option C. Now move on to the question number 8. So question number 8 said that a concrete pile of 450 diameter is driven through a system of layered cohesion soil. The length of the pile is given 16 meter. The following details are available. The water table is close to the ground surface, and uh, top layer properties are given. Layer 2 also given. Bottom layer properties also given. To find the ultimate. So water table is given at the ground surface, but the soil is cohesive soil. So there is no effect of water table. So we find out the skin friction first for different layer. Here it is FS, QF1, QF2, and QF3. So QF1 is equal to alpha 1 C1 pi D L1. QF2 is alpha 2 C2 pi D because diameter is same, L2. And alpha 3 is so QF3 is alpha 3 C3 pi D L3. So L1 is given 8 meter, L2 is given 6 meter, but L3 is not given. The total length is given. So subtract 8 and 6 from 16 and get 2 meter. So L3 is 2 meter. Alpha 1 given is 9.9, alpha 2 is 0.75, alpha 3 is zero point 0.5. C1 is given 30, C2 is 50, and C3 is 105 kilometer per meter square. So put all these value in and get the answer. So QF is QF1 plus QF2 plus QF3. So put all this value. Alpha is zero point 0.9 into C is 30 into 8 into 3.8 last point 75 into 50 into 6 plus 2 into 105 into zero point 0.5 into 3.1 into the diameter is given 0.45. So answer is total QF is 1714 sorry 771.49 kilonewton. Now find out the QB. So for finding out the QB we use the formula 9C pi by 4 T square. So here C value is the bottom layer C value. Uh, so which is C3. So answer is if we put all this value, that is C is here 105 and pi by 4 into D is 0.45 meter square. So answer is 9 into 105 into 3.14 into 0.45 square divided by 4, which is equal to 150 kilonewton. Add both the result, QS plus QB, get the total ultimate load, which is equal to 921.70. I'm writing 921.70. So the closest answer is here option A, that is 922.19. The correct option is option A. I think it is okay to everyone. For layered soil, just there is no change in the formula of QB, but there is a change in QF because for each layer there is different QF because QF acting on along the length of the pipe, and for different soil there is a different force, resistance force acting on the length of the pipe. So we divide this length layer or length of the pile according to the layer of the soil and find the QR, QF1, QF2, QF3 After that, add all this value and get the total QF. And then we find out the QB by our basic formula. And if you add this QF and QB, we get the total ultimate load. Now, move on to the question number 9, which is linked to the question number 8. So, question number 9 is said to find out the safe load where factor set is given 2.5, and we use the data of the question number 8. So in question number 8, we find out the total ultimate load. This Q is equal to 121 or 122,470. We have to find out the Q safe. Q safe is equal to nothing but the Q ultimate divided by the factor of safety. Q ultimate is equal to 1.70. The Q factor of safety is 2.5. So divide it with the 2.5 and get 368.63. So the correct option or closest option is option number B. So our correct option is option B. So I think it is solved. Now our last question of our today's session, because it is already 5:59. So we have to stop after completing, sir. Solve this question number 10. I am providing you the previous year assignment problem of question number 2023. You can go through the question and solution. First try to solve by yourself and then solve. If required any help required, you can go through the solution. Now question number 10, it said that a precast concrete pile of size 45 by 45 centimeter square given. That means the size is 4.45 meter and driven into stiff clay. The unconfined compressive strength of clay is given 200 kilonewton per meter square. So QU is given 200. So we know that cohesion, undrained cohesion CU is equal to QU unconfined compressive strength divided by 2. So cohesion is equal to 200 divided by 2 kilonewton per meter square, which is equal to 100 kilonewton per meter square. And then the length of the pile, we have to find out. As a working load, safe working load is given 400 kilonewton with using the factor of safety 2.5. And alpha is here using 0.4. So we know that Q safe is equal to Q ultimate divided by the factor of safety. So Q ultimate is equal to nothing but the factor of safety multiplied by Q safe. And again, we know that Q ultimate is equal to, for this type of square pile, alpha into C for friction, 4BL plus friction, it is alpha C 4BL, and for end bearing it is 9C B square. And this is equal to the factor of safety multiplied by QC. So put all this value here to find the length of the pipe L. So factor of safety is 2.5, alpha safe is given here 400 kilonewton, alpha is given zero point 0.4, C is we find out 100, and 4 into B is here given 0.45, and we have to find out, plus 9 into C is again 100, B square is 0.45 square. Put all this value and find the L. 2.5 into 400 minus 9 into 100 into 0.45 square divided by zero point 0.4 divided by 100 divided by 4 divided by 0.45. So L is equal to 11.357. So correct option is here option A, 11.35 meter. So our correct option is option A. So we completed or solved all the assignment questions of 2020. You can go through the 2023 assignment problems and try to solve this year assignment problem. And these are the very interesting problems given. Uh, if you solve this, I think no extra problem you have to solve regarding to this chapter, today's class, and try to solve by yourself, and then if you not, then you take the help of the solutions. Now there is 6:03 p.m. So we have to stop now. It is already 2 hour completed our meeting, so will meet again in next week. That is that is week 9. So from my side, we I stop now. So thank you everyone. Good night, and we will meet again in next week, which is week 9. With just 4 weeks are left. After 4 weeks, there is one extra session also. That means total 5 classes are remain from here. So thank you everyone. I am stopped now. Thank you.